Okay. So 3 things due. The last homework is I have asked the graders to grade it so you can get feedback. But it's more like, did you give it a try? But I would like you to look at the feedback if possible. So that homework, and then showing up for the last lecture. So there's 2, we have the 2 to 3 section and the 3 to 4 section. You can show up to either one, and I'll start at the beginning just like a regular class. So when I get done, then people that have a final after the class, they have time to prepare for it.
What day is it?
I have to look that up. Oh, hi, Raul. I didn't see you there.
Hello.
They have you as graduating this quarter.
Yep, that's the hope.
Oh, cool. Okay. What was I saying? I forget what I was saying. Yeah, but yeah, homework, interview, and showing up for class. And the classes will be whenever the final exam was scheduled. And you can show up for either the 2 to 3 section, Monday, Wednesday, Friday, 2 to 3, or Monday, Wednesday, Friday, 3 to 4, your choice. I think that's it. Oh, somebody pointed out that the answers were wrong for the homework. So I fixed that in green font. So that's been posted. There's one more thing I thought. I can't remember. Are there any other questions on the rest of the quarter? Oh, yeah. And the graders are free at the end of the week. So if you turn it in Thursday or Friday, that's plenty of time to give them to check off your homework. So make sure you do grade on whatever else you have to do, and then you can work on the homework if you want. Anything else? Okay, let's see. Let's see. Okay. So today, the goal was all of this. But didn't quite get there. I didn't do these topics down here. I didn't do these topics down here, but they actually fit better with talking about this last topic of feedback than with the topics that I talked about today. So I think it's actually okay. So these are the topics for the day, minus these down here. And just talking about basic things about feedback. We kind of jumped into Barkhausens, I think, like maybe 2 lectures ago for you. I'm not sure if we actually got to Barkhausens, but let's go back and just talk about the first stuff about feedback. So far, again, up to the end of last lecture, we were talking about just the frequency response of a single amplifier, not with feedback. So where the poles are, where the zeros are. So we found the poles by using the quick method, and we found the zero by doing small signal analysis with capacitance in the small signal model and going through a common emitter analysis. Poles happen between 2 stages. So in a regular 3-stage op-amp, you have the input stage, you have the gain stage, and you have the output stage. And between the input stage and gain stage, you have a pole. And between the gain stage and the output stage, you have a pole. So you have 2 poles from that system. But let's say you have, oh, why am I doing this? So I got the pen. What I did was I pulled I think the battery was just loose inside the pen. I think that's what was going on. I shouldn't say anything, but it's been pretty good since I kind of bent the spring out, so it was really pushing it in, pushing the battery against the contact. So here's our magnitude plot. And this right here is whatever your lowest frequency pole is. And that's your underlying op-amp. So your op-amp has some large gain out to a certain point where the low-pass filters start to kick in and you start going down by your minus 20 dB per decade. Okay. When you hook when you hook an op-amp up with feedback, for example, when you hook it up with feedback, you'll never get a larger gain than your underlying op-amp. The feedback block right here is a multiplier, and whatever signal comes into it, that signal gets multiplied by whatever's in this block. And this block, the gain of this block is less than 1. So when V out comes in, it comes out as a smaller signal. So gain will never increase when you hook something up with feedback. So the gain will actually drop. So your new gain of, we'll call it gain 1, will drop. And if you were using an op-amp with this underlying frequency response, you can't ever go outside this boundary. You can't do better than what's this black line right here. You can't do better. You can't get a higher frequency for a gain, and you can't get a higher gain for a frequency. It's limited by your op-amp. So if you hook this up with feedback, then your gain drops, and where you hit that boundary, now your new op-amp with feedback follows that line down, because it just can't perform better than your underlying op-amp can perform. Okay, so this is, let's look at a couple of terms here. From here to here, that's your bandwidth. Of your underlying op-amp. Okay, what happened to the bandwidth when you hooked it up with feedback? I missed what was said, but I will guess.
Tristan was trying to say something.
It increases it?
Increases it. So it makes the bandwidth wider. So that is called wide banding. Wide banding is the op-amp amplifier. And all that means, it's kind of like degeneration. So degeneration, you add degeneration, you say, oh, I have a wider range of inputs I can give it. You just killed your gain. That's how you're doing it. This is the same thing. Oops, you killed your gain, but hey, now I have a wider band of frequencies I get a constant gain at. So this is wide banding, and this is your new bandwidth for gain of 1, or gain number 1. Okay, something really interesting happens here. Let me circle the terms that are good to know so far. Bandwidth is good to know. Wide banding is good to know. An interesting thing happens on every point on this line right here. Turns out, if, let's say I change the value of F here, then I have some gain 2. So I have gain 2, and let me write this as F1, and then right here, call this F2. The neat thing happens along this line. Your gain 1 times your frequency 1, in other words, the bandwidth of when you have gain of 1, will equal your gain of 2 times your frequency of 2. So if you multiply the bandwidth times the gain, you actually get a constant along this line. And I did the math in the video, so if you want to see that math, or an example. I didn't really do the proof, but I did an example to show that that's true. So if you hook this up with feedback to get a particular gain, if you bring it all the way over until it hits that line from your underlying op amp and draw a line down to find a frequency, turns out every point on this line will equal a constant. And y'all, have you seen this in lab? What this is called? Maybe not. It's called gain, because you're multiplying the gain times the bandwidth. And P, sometimes it's on there, sometimes it's not, but gain bandwidth product, because you're multiplying them. Okay, another term. And this is a really useful metric that you can find on most amplifier data sheets, most if not all. I hate to say all. Again, it's my thing where I'm sure there's an exception someplace, but any data sheet worth its what? What's a good word to finish that sentence? Worth its
weight in gold. That's not good, but it's all I can think of.
Okay, worth its weight in gold. We'll have the gain bandwidth product on the data sheet, and that says, okay, if I buy this op amp and I need a gain of 100, let's do it like an example. Let's say I know that I have an op amp. Let's say the specs that the data sheet says gain bandwidth product equals 100K. And I know that I need a gain of 1K. So your boss comes to you and says, build a board that has a gain of 1K. And then if you have these two pieces of information, you can say, well, if I know that my gain, if the gain bandwidth product of the underlying amplifier is 100K, then I feel like painting this. There we go. Now I'm happy. Then what you do is you know that gain times bandwidth equals the gain bandwidth product. You know the gain is 1K as a bandwidth equals 100K. And so you know your bandwidth will be 100 hertz. Okay. So this is really useful if you need to know if you can satisfy a particular specification. In your first week of 409, depending on who you have, you may get a homework problem. Might even be in the lab too, but where I'll scroll back down in a second, where you're trying to get, you have your kit with a fixed number of chips. And you're trying to get a gain of this much at this frequency. Can you do that with the op amp that I drew with the black line? No, it's outside of that black line, so there's no way you can get that gain at that frequency. But if you had a pile of these, amplifiers, could you do that, have this point on your graph, on your gain? What happens when you cascade two amplifiers?
You increase their gain.
Yes, so you'd actually be starting out up here. I'm not going to draw it, but so if this is the underlying op amp, your gain would start out here. At the pole, now you have a pole from your first amplifier and your second amplifier, so you'd be going down at minus 40 dB per decade. But you can get that point now. So even if you have an amplifier that can't have that performance. If you have two of them and cascade them, now you possibly can. Okay. Good for bandwidth, gain bandwidth, and widebanding. Okay. So let's go to a little more in depth of where this line is, and a ton more vocabulary. That's the thing about diff pairs and this stuff. The vocabulary is some of the hardest part. And for those of you that have had 302, you've probably seen this before. That's supposed to be a minus there. Does that look familiar from 302? Not so much? Okay.
Yeah.
All right. So this is a nice model for an op amp, because with an op amp, for example, you might have this configuration, and what's actually amplified. Let me get rid of this a little bit. Well, no, I'll leave this in. What's actually amplified is your VI plus minus VI minus. That's what gets multiplied by AV to give you V out. So it's the difference between the two inputs that gets amplified. And if you look over here, this circle right here, it has a plus on the V inside, and supposedly you had a minus there, minus on this side. That means it's taking the difference between these two signals. That's exactly what an op amp does. So the input of the op amp is represented by this differencing block right here. And then that difference gets multiplied by the gain and becomes V out. So you can see how it kind of matches up with the op amp. Okay, so let's do a little bit of math here. So V out, it's this block, the feedback block right here. It's actually like an amplifier. It takes whatever's on its input and multiplies whatever is on its input by F. Okay, this block right here takes the difference between these two signals and it goes on this wire. So let's do that. V in minus F V out. So that's what goes right here. And then this whole thing gets multiplied by the gain. So you have AV V in minus F V out. So if you start here and go around the loop, you know the value at this node is AV times V in minus FV out. But you also know that this node is V out. So you can set those equal to each other. You can say V out equals AV V in minus F V out. And we want to find gain, so we want to have V out over V in. So I'm going to move all the V outs to one side and keep V in on the other. So we have V out, and then there's a minus sign here, so we move it to the other side. It's a plus F A V V out. So I'll move this whole thing over there, and then the only thing left on the right side is AV V in. And now I want to get V out over V in, so I can factor out the V out right here. AV V in, and then what I actually want again is gain, so it's V out over V in. So I can divide both sides by V in and divide both sides by 1 plus AVF. And I get that. Does this look familiar? Okay. All right. So terminology here. Well, actually, let's go one more step. What's the ideal gain of an ideal op amp?
Infinity.
Infinity. So if AV, which is the gain of the op amp, is infinity, what's this go to?
1.
Almost. You're right. The AVs cancel out, but what's left in the denominator?
I guess 0 then.
Well, if AV is gigantic, then AVF is going to be much bigger than 1, so you can ignore that. And then you end up with AV over AVF.
Just
So 1 over F.
1 over F. Yes. And that's the magic of op amps with feedback, is they 100% depend on the feedback block. It doesn't matter what the gain of your op amp is, as long as it's big, it will still give you this great result. So you were, in lab, you had like gains of 10,000 or 100,000 or a million or something. That's all you need. As long as that gain is big, if you hook it up with feedback, the actual amplifier won't matter anymore. And it doesn't matter. Did I already say this? I forget whether I said. Excuse me if I'm repeating, but it doesn't matter if it's linear. Doesn't matter if it's all squiggly. As long as it's, big gain, this will still work. Whoops, is somebody trying to hack me? Oh, okay. All right, so because we haven't had enough vocabulary yet, let's do more vocabulary. And again, if you've had 302, you might have heard all of these. But let's do loop gain. So the loop gain is equal to AVF. And the loop gain says, okay, if I go through all the stages that multiply my signal, what's my gain? So it's pretty much from this point to this point. It's where you cut the feedback and just go through your gain blocks. And this is seen so much, it's given a special name. Okay. And then next is open loop gain. And that's if I cut the feedback and I change VN, how much does V out move? And you can see if you cut the feedback, if you open the feedback loop and you change VN, then you're just going through the amplifier itself. So that's just AV, and that's from V in to V out. And then when you put everything together, connect up the feedback and all. For the entire system, they generally use a capital AV. And then the last definition is the feedback factor. And that's what my textbook called it. There may be some other names out there. And that's just the gain through your feedback network. So all 4 of these are commonly used in discussing amplifiers. So if you have an interview with a company that maybe builds amplifiers or all, it might be worth your while to come back and look at these definitions. And just one more thing, and I forgot to say it in the other class. So this gain right here, it's the gain of your op amp over 1 plus the gain of your op amp times the feedback factor. And when you just to mark it on the graph, I'm going to scroll up, I'll scroll back down. this gain 1 right here, that is AV over 1 plus AVF equals AV over 1 plus T. That's your new gain. So whatever your oh, and then again, if the gain is large, then this is approximately 1 over F. That's your new gain. That's your G1. So your G1 equals approximately your 1 over F. Okay, questions up to there on just definitions and stuff like that? Okay, so we're basic vocabulary. So let's go look at Barkhausens and compensation capacitances. Okay. So I think we did Barkhausens or just brought it up like 2 lectures ago, but we didn't talk about it last lecture. Is that right? Or did I not bring it up 2 lectures ago? Maybe?
You've brought it up, I think, but I don't remember what day. Unless I'm thinking about lab.
Okay. So let's do that. Again, the most traditional op amp you'll see is a 3-stage, where it has an input stage, a gain stage, and an output stage. It might have some common collectors or something thrown in there, but most basic is input stage, gain stage, output stage. And again, that's 3 stages, so there's probably going to be, there is a pole between the input stage and the gain stage, and there is a pole between the gain stage and the output stage. So those are 2 poles right there. So if you drew out the magnitude plot, you've got your 20 log of gain of your amplifier. This would be, has to be with feedback, yes. And you might have your original pole, your first pole, and your second pole. And this is your minus 40 dB per deck. This is your minus 20 dB per deck. And then we've done it a few times, so I'll just draw it in. The phase shift, if we're assuming we're starting at 0, 1 over RC1, 1 over RC2. So a decade before it starts to drop, and a decade before the second pole it starts to drop. And the first one, it's at minus 90. Second one, it's minus 180. Okay, so there's, just as a reminder, this only matters when you have feedback. We don't care about this if you don't have feedback. But let me take one step back before that. If you have an op amp set up with feedback, for example, see, you always want negative feedback. And we talked about what negative feedback was last time, but you always want negative feedback. So if you move Vn up, Vn plus up, Vn minus, if it's negative feedback, will follow that a little bit. Okay. With positive feedback, if you move Vn up, negative feedback goes, the inverting input goes down, and it actually makes the difference between Vn plus and Vn minus bigger. So from last time, are there any questions on what negative and positive feedback are? Okay. So let's say when your circuit's working normally, this is your feedback. So this would be VI minus. If you flip that 180 degrees, that actually becomes positive feedback. So if this is negative feedback, if you flip it, this will become positive feedback because it's moving in the opposite direction than it would if it was negative feedback. And if you're flipping it 180 degrees, that's right there. That's your 180 degrees phase shift right there. You've actually flipped the circuit, and now what used to be positive feedback is now negative feedback. Whatever, backwards. What was negative feedback is now positive feedback. And so Barkhausen's, I forgot to talk about phase margins. Darn it. I messed up on the first lecture. I left out some terms. But if you drop from 180 degrees phase shift and your gain is greater than 0 dB, that means the signal you're sending back is bigger than your input signal. And that causes problems. If at 180 degrees phase shift, your gain was less than 0 dB, in other words, the signal you're sending back was much smaller than your input signal, then it's probably not going to be a problem. So Barkhausen's criteria says at 180 degrees phase shift, at 180 degrees phase shift, gain 20 log of your gain should be less than 0 dB. If it's not, then your circuit is probably not going to work. Okay. And if it violates, let's write it over here. If it violates Barkhausen's, then circuit is unstable. So Barkhausen's criteria is this over here. And if it violates Barkhausen's criteria, then the circuit is said to be unstable. So more vocabulary. And if it doesn't violate Barkhausen's criteria, what do you think it's called? Whatever.
Stable.
Stable. Okay. So looking at this graph, I think we talked about it before, but how can you make, more vocabulary I forgot to put in. This is the dominant pole. And all that means is that it's the lowest frequency pole in the system. And this is the secondary pole. The secondary pole is the one that causes that 180 degrees phase shift. Okay, so this example right here violates Barkhausen's. So this graph makes me think, oh, this circuit could very well be unstable and oscillate or just go to VDD or just go to ground. So how can you make this stable? What's the best way to do that? Most common way. How could I change this graph to make it stable?
Increase your Or I guess decrease your RC2 value. So like reduce capacitance or resistance.
Okay, so that would work great, because then the magnitude would be able to drop farther, and then you'd have your second pole, and your 180 would be way out here. So that's perfect, but it's very hard to reduce resistance and capacitance. You could turn up current, but sometimes that hurts your gain a little bit. So in general, it's hard to do that. It's hard to reduce stuff. So how else could you do that? That's perfectly valid, but it's hard to do.
Shift the dominant pole back.
Yeah, shift the dominant pole. So how could I do that?
You could add capacitance across your input output of your second, or like of the second stage, I guess.
Okay, yeah, so if you increase your capacitance and you say, well, I also could increase my resistance, you could, but that's also generally harder to do than just throwing a capacitor on your circuit. So the simplest thing to do is increase your capacitance. So I agree. So if you increase that capacitance, then that moves that pole out there. Now your gain starts to drop earlier. And by the time you get to your second pole, now it's stable. Now at 180 degrees phase shift, this moves over, but at 180 degrees phase shift, now the gain's less than 0 dB, and it's probably stable now. Okay, so let's see, 47, we're in good shape. So what should I leave up visible? Don't freeze, don't crash. Oh, good. Okay. If I scroll, will it mess people up? I can't see anybody. So I know it's hard to ask questions when I only see like half of all the pictures up. So let me do a, because you're a step ahead of me. So I've got our input stage, and then let's say we have, and I drew BJTs, but it's exactly the same for MOSFETs. And I use NPNs just because they're friendlier to look at. And you have V in, and here's your V out. We'll call this a V1, V2. So one thing here before we go on is this whole thing right here, it equals an op amp. And with an op amp, you know if you raise this input, V out goes up. So I need to figure out first which is the inverting input and which is the non-inverting input. So any guesses on which is which? Left or right is the non-inverting. So if you can't see it right off
Left
the
is non-inverting.
no,
Left is inverting. Sorry, because there's a
yes, you got it. Yeah.
hole in
So
between.
if you can't see it right off the bat, like a good way to do it is to say, okay, I'm just going to move one of them up and see what happens. So if I move this side up, the voltage on this input up, what happens to V1? Does it go up or
Goes
does it
down.
goes down? Yeah, because these are just two common emitters stuck together. So this side is a common emitter. Move the input up, output goes down. What about V2?
It'll go up.
It'll go up. Yeah, common emitter is inverting, so this one go up. And common collector, is it inverting?
No.
No. So this also goes up. So when this input goes up, V out goes up. So this is the non-inverting, and this is the inverting. Okay. And then that was a few people were when they were trying to hook their op amps up as voltage followers, that I saw a few that had these inputs switched, and once they switched them, made this one the non-inverting input, then it worked okay. But if you have the inputs switched, these circuits won't work. Does that just turn it into positive feedback? It might just turn it into positive feedback, and your circuit will fail. Okay, so we've got that now, and I'm just going to say this is, how many minutes do we have? 10. Wow, we're doing good. The dominant pole, I'll just say V1 is the dominant pole. Remember, it happens between two stages, so it'll be here, and we'll call this the secondary pole. So what Casey said is the final answer, but the simplest answer is say, okay, well, I need to move that pole down, so I'm just going to add a bunch of capacitance to that node. And that moves the dominant pole over. So that's a totally valid solution, but what Casey said was, how about putting it here? Why is that a better answer? Why is that a better answer?
Because the capacitance changes relative to the gain. So you could use a smaller capacitor and it'll seem bigger based on the gain that you're at.
Exactly, yeah. So if the gain of this is 100, you get to use 100 times smaller capacitance if you put it here than if you put it to ground. Now what effect are you using to do that?
The Miller effect.
Miller. And it's transistors are very small on integrated circuits. You know, the single digit nanometer now, that's insane. For a capacitor though, the process that we're using we have a few projects going right now, a 1 micrometer by 1 micrometer square capacitor, in other words, parallel plate capacitor with both plates of this size, it's actually in the attofarads. Does anybody know what an attofarad is?
Is that a really, 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 really small capacitance?
Yeah, I think it's 10 to the minus 18th, but I didn't do my homework for class. So it's 10 to the minus 18th farads per micrometer. And right now with, transistors that are a fraction of a micrometer, you can put, 100 transistors in a micrometer, no problem. And you can't even get, a nanofarad, in that same area. So you can imagine, so if you wanted to, let's say this was you have to always check with the fabricator, the people that fabricate the ICs for these numbers, but let's say you have 7 attofarads per square micrometer. If I make this 2 micrometers by 1 micrometer, now I have a capacitor of 14 attofarads. So it's proportional to the area. So you can imagine if you needed a microfarad, you can't put that on chip. It's so big, it would take the entire chip and more to just have a capacitor of any size at all. That's one of the decisions you have to make when you're designing integrated circuits. If you have a capacitor or an inductor or a resistor in your circuit, you have to figure out whether that's going to fit on chip, or you put it on the data sheet and tell the user to add the resistor externally, or the inductor or the capacitor. Okay. So yeah, this trick with the Miller effect, now you can use a much smaller capacitor and make it look really big. Okay. Once again, we finished before the other class. Any questions on this? Let's do terminology. Actually, I think we got all the terminology. I think we've got the terminology. Any questions on Barkhausens or dominant and secondary poles, or anything about the homework? I'm guessing nobody's looked at the homework. Okay. It might be too much. I'm going to go back and see if there's something I can remove and still give you practice. That's probably good that nobody started. What's that?
Sorry. I was to say I've got a question. Is
Okay.
it is it possible to use a transistor as a capacitor?
Yes.
So would that be something viable to replace that capacitance with then? Since it's
Yeah. I can't remember numbers for them, but as you change the depletion region, you know the capacitance is proportional to area over distance.
Mhm.
That distance is the width of the depletion region. So that changes. Also, remember that when you're in the forward active region or the saturation region for MOSFETs, I can't, since I can't see myself, where you have the collection of electrons on the source side of, say, an NMOS, as you change the voltages, that covers more of the channel and less of the channel. So there's various different ways to create capacitance with a transistor. I know, is it femtopico farads you can produce with a few transistors? With a large transistor, you could probably do femto or picofarads.
You still can't get to nano though.
Yeah, it'd be pretty big, but you're right. It might be more. The one thing about it, so you can implement resistances with transistors and capacitance with transistors, but they're generally higher tolerance. So if you want a really active, a really accurate capacitor or resistor, you generally don't implement that with a transistor. And any other questions? Okay. So next time, the goal is we'll talk about the naming. That'll just take a little bit. That'll take care of this and this. That'll take a few minutes. But the main goal of meeting during finals week is how the feedback block actually loads your amplifier and how your amplifier actually loads the feedback block. And generally, if you have a high R in and a low R out, you don't need to worry about it. So generally, that's maybe this topic isn't as fun as I thought, because if you make a good op amp, then it's not really of importance. But so it's only important if you make lousy op amps. The next topic is only important if you make lousy op amps. But you all made great op amps in lab, right? Thumbs up on that. Okay. So that's all I have. If there's questions or anything else, then I have like 15 minutes to the next meeting, so I'll hang around a bit if there are questions. We had a great person lined up. We were going to hire her, and the dean took so long to respond to our request that she signed with another university. So we've now lost, over the last year, we've lost like 4 or 5 people that we all had lined up to hire. Pretty sad. So we're meeting again and trying to figure out what we can do. She was going to teach 409, I think. She was very good.
I feel like that's such a sad reason to not get a job at that place, just over the employer not getting back in time.
Yeah, but the funny thing is, then the dean gets mad at us for having a failed search. It's like,
yeah, that's
we worked really hard to get you this candidate. I'm sorry, I'm ragging on the dean again. I'm sorry.
No, let him have it. We don't mind.
Oh.
Except you might want to remove it from your recording. I don't know.
Oh, shoot. All right. I just got to